groupoid gauge theory, you have like a scalar field, and you have a one-form potential, and so you have kind of two levels again, because you have the covariant derivative of the scalar field and the curvature, right? So in groupoid gauge theory, you get this very similar situation. You also need these adjustments and this technology actually in the case of groupoids. Okay, so what's subtle about high gauge theory? Let me start very simply with something that you're probably all familiar with, or at least have heard many times in private seminars. So homotopy Mauer-Cartan theory of L-infinity algebras. You all know an L-infinity algebra, right? So in the bracket picture, we have a graded vector space, and then you have a differential on this graded vector space, so you get a cochain complex. And then you additionally have these graded totally axisymmetric multilinear products. So essentially, you can have I inputs mapping to one output. They have a specific degree. And they generalize differential graded Lie algebras in that they satisfy not quite the Jacobi identity, but the Jacobi identity is violated up to homotopy, and the violation is encoded in these higher brackets, and it has higher Jacobi identities and so on. So they're just a homotopy version of Lie algebra. In addition, it's usually nice to have a metric or cyclic structure, in particular if you want to do physics with them, but it's just an obvious thing, right? You take true L-density L-infinity algebra, you map to your ground field, whatever that may be, your R for simplicity. Should be non-degenerate, graded symmetric, bilinear cyclics. But cyclicity just means that, you know, if you take one of these higher products and you leave one slot open, that acts as a derivation on this and produces zero. It's the obvious definition, right? There's nothing subtle about this. Okay, and the nice thing about these homotopy Mauer-Cartan, homotopy Lie algebras is that they come with their own gauge theory. And this is homotopy Mauer-Cartan theory. You remember the Mauer-Cartan equation for differential graded Lie algebras up there in the top, right? So you have the graded Lie algebras, that graded whatever, differential on this, and then you have the Mauer-Cartan equation. If you look at objects of degree 1, it makes sense, right? And you can generalize that. You just generalize that in the obvious way. The differential is mu1, the B bracket becomes mu2, but then you also insert all the other brackets, and the flatness would mean that this is equal to 0, right? So that's an obvious generalization. You get high gauge transformations between these by looking at homotopies between such Mauer-Cartan elements. You get Bianchi identity, and finally you get this equation actually from the homotopy Mauer-Cartan action as well, right? And that's actually dually described by the BV formalism, if you know that, so there's very close connection over there. But the interesting thing is, yeah, you have the kinematic information of a gauge theory, and you also have some equation of motion and even action principle alignment, right? That's what you have if you have a cyclic L-infinity algebra. Yeah, and as a quick example, we can look at 4D Chern-Simons theory, which is already something that probably a little bit outside of what one usually does. And the idea behind that is simply, well, you can always take a commutative algebra and Lie algebra, tensor them together, you get another Lie algebra. And the homotopy version of this statement, or a special version of the homotopy statement of this version, statement is you have a DG commutative algebra, tensor and L-infinity algebra, and you get again an L-infinity algebra. Right? So we can use that. We can use at our DG commutative algebra, we just use the differential form from some manifold. And as an L-infinity algebra, let's use a two-term L-infinity algebra concentrated in degree 0 and -1, for example. And then this tensor product has a natural L-infinity algebra structure, which is very simple. Namely, the differential on the tensor products is given by the Devan differential plus the differential in our L-infinity algebras, and the other products are not really deformed. There's a few signs that you have to take care of, but otherwise nothing. Okay, so what is the gauge potential? So what is the analog of this A in degree 1 of the tensor product? Well, if you want something of degree 1 in the tensor product, it can be of degree 0 in the L-infinity algebra, degree 1 in the forms, of degree -1 in the L-infinity algebra, and degree 2 in the differential forms, and then it will be of degree 1 in the full tensor product. So you get essentially L0 value 1 forms and L-1 value 2 forms. And because of the form degree, I can now split things, right? So I can split the homotopy Mauer-Cartan equation like this, and for a 2-form curvature and a 3-form curvature, and the equation just says, the flatness equation just says that it's 0. And then you derive the Bianchi identity, and it looks like this, right? So it's like a covariant derivative acting on H is given by these two terms. That's all nice and fine, and you get this. And you get also this Bianchi identity typically if whatever way you naively derive high gauge theory, that's a typical thing that you arrive at. But then you look in the physics literature and you see that this is actually not quite what you expect, because in supergravity you get the H is FHF, right? That's the so-called Green-Schwarz anomaly cancellation condition, and this is what we're actually after, right? So something has gone wrong or something is problematic there, right? Okay, you could argue that's 4D transcendence theory, but even if you forget about the dynamical principle of what actual field theory you have, just the kinematic information, this Bianchi identity will always stay the same, right? So that's an issue that we need to resolve. That's a great mystery, and it took me forever to understand what's really going on. Okay, anyway, let's go to an alternative picture, and let's see, maybe the L-infinity was a little bit too naive. We are talking mostly about flat connections in the L-infinity picture in the Motivimau-Catan theory, and that's indeed the problem that's a little bit underlying. Let's look at a different way of defining higher connections, right? So, for example, we can look at the splitting of the Atiyah Algebroid sequence. That's certainly a good way. I mean, Atiyah, we can always trust him. So that's the Atiyah Algebroid sequence that we have up there, and the splitting, that means the map from Tm into the Atiyah Algebroid as a map of vector bundles, as a splitting of vector bundles actually, gives you a connection on the principal bundle. There's a slightly simpler version that shows you a little bit more detail what's going on, which is essentially when you go to an open patch, you know, where this Atiyah Algebroid trivializes, and you just work locally in the neighborhood of the point. And you find that in early work by Platon, and then Karl Strobel worked on this, and Dati and Jim Stashev, they took this, and this is actually the picture that you find in their papers when they do explicit things. So locally there, a connection is just a map from the tangent bundle into the Lie algebra, right? Because you have the tangent bundle, and if you locally work, you know that your bundle decomposes in the tangent bundle. You get the Lie algebra as additional fiber, so you have the identity, of course, on the tangent bundle, and then you get the map into the Lie algebra. Nicer to describe that is as follows. Both the Lie algebra and the tangent bundle have dual Chevalier-Eilenberg algebras. So that's a dual differential graded commutative algebra to them. So in the case of the Lie algebra, the Chevalier-Eilenberg algebra is just generated by a coordinate function on the Lie algebra plus a differential that's squares to 0. You see, the only differential that I can write down on Lie algebra is necessarily, if it has to be degree 1, it has to produce something quadratic here. So I should probably slow down a little bit. So you have this particular coordinate function. You take the Lie algebra, you shift in degree by -1, you dualize, so this thing has degree 1. This has to have degree 1, because you want a differential of degree 1. So the total thing has to be bilinear in its size. They're all coordinates on vector space, everything has to be linear, that's the only thing that you can write down. You combine it with structure constants, and of course you recognize the structure constants of your original Lie algebra. Now the condition for this to be differential, that it squares to 0, is essentially is precisely the Jacobi identity for these structure constants. The Chevalier-Eilenberg algebra for the tangent bundle is just the uncomplex with the undifferential and usual product. And then gauge potential can be seen as a morphism of the differential graded commutative algebras. Well, a morphism of graded commutative algebra, sorry, we forget the differential at first, from the Chevalier-Eilenberg algebra into the differential forms. And then you see the degree 1 object needs to be mapped in a particular 1 form that defines for you the potential, the Lie algebra valued local connection form. And the curvature is just defined as a failure of this particular A to be morphism of differential graded commutative algebras, right? So you're saying, okay, you want, ideally, if there was a morphism of differential graded commutative algebras, the differential will commute with this A star, and you just write down what the failure is, and you recognize the usual expression for the curvature, right? So it's a very nice way of defining connections, and then you also see how you do that for higher connections, because you can replace your Lie algebra with an L-infinity algebra, use the corresponding Chevalier-Eilenberg algebra, and you just consider these maps, right? So that's all very nice, straightforward story. Yeah, but this all gives you something. Yeah, if you want to with non-flat connections, it's nicer to stay within the category of DG manifolds and DG morphisms. And what you can do to do that is essentially resolve this failure of being not a morphism of DG algebra by doubling things. So instead of just having G1, you go to the corresponding Bay algebra. That's the Bay, also the Chevalier-Eilenberg algebra of inner derivations that you considered. So instead of having just psi alpha, you have a second copy that's shifted. And then there's a natural way of continuing, of extending the Chevalier-Eilenberg differential onto this Bay algebra. using this shift isomorphism. So this is what you define and you continue it in the unique way. And yeah, and then you can indeed derive the connection and its curvature as morphisms from the Weil algebra, e.g. CA morphism now from the Weil algebra into the differential forms. And nicely, the differential forms are the Weil algebra actually of the trivial Lie algebra that is just the manifold itself, right? But that's side remark. What do you get? Well, psi alpha needs to map to the potential, and a shifted version of psi alpha needs to map into a particular expression. And because it's a DG morphism, this maps precisely into F alpha, which is then defined by the DG relation to be really the curvature that you used to, right? And then in addition, we need that Q on this has to be mapped to 0, and that's just the Bianchi identity. So you do get the complete kinematic data of a gauge theory from this picture at a local level, right? So you get the connection, you get the high curvatures, you get Bianchi identities. And if you look at homotopes between such maps, you also get gauge transformations, right? So everything there comes automatically. Yeah, you get also topological invariance, and if you're interested in this whole story, then you can look at Saty Schreiber-Stashev in 2008. They developed that all a long time ago.
Sorry, may I make a remark?
Yeah.
I think this was really our construction, and there was a point that Urs was sitting in our lectures, and we had quite some fight about this. But I think it was definitely us before.
Sorry, yeah, okay. Sorry, maybe I'm misrepresenting. Sorry, Thomas, is that you?
Yeah.
Hi. Okay, so I thought I recognized this one. I knew this part of this course, yeah. And you're here. You mentioned the college model there in the middle between Carton. I thought that this was actually originally Carton, so I certainly saw the Weil algebra in Carton, but it has been a while since I looked at the papers, at the original papers.
Yeah, but in the generalization where you have the Q bundle.
You know, this seminar. Oh, yeah, I forgot the title, sorry. But I thought that this was, yes, absolutely. Yeah, I'm sure that this is in your papers as well with the Weil algebra, right? So this is more reference. I'm sorry, apologies if I get the history wrong. Usually in the papers I cite everybody. I hope I cite you wherever. Otherwise, Thomas, please complain to me and I'm immediately.
Okay.
Okay, so, and then now the question is, after all of this work, if you actually do this and you go through this for Lie2 algebra, so for what we did here with 4-dimensional transscience theory, and you compute what the Bianchi identity is, it's still the wrong thing, right? So the Bianchi identity that we know from supergravity and we would like to get is this DH is F wedge F versus DH is -1/2 DAAA, which you see, and this is of course a much nicer expression on the left-hand side than the right-hand side. Apologies for everybody online. I'm realizing that I'm pointing on the board and so on. So I'm sorry. Perhaps I should use the well, that doesn't work either. But okay, I'll try to describe it works what I'm doing. So anyway, you get still, if you follow this procedure, you get the wrong Bianchi identity. And the solution that was found, and that's a little bit hidden in the paper, it's definitely there, but it's not really highlighted enough in my opinion, or why you do that. What you can do is you can actually, instead of using the Weil algebra as you get it on the nose, as I described it before, you can perform a change in basis in the Weil algebra, so you use different generators, and that allows you then to get the correct notions of curvatures that you want with the correct physical interpretation, right? So you need to do this transform in such a way that the Weil algebra projection to the Chevalier-Heinberg algebra is actually preserved, and there's an additional condition that you get the right invariant polynomials. Let me quickly show you concretely what happens in one particular case. That's a so-called string Lie2 algebra, which is an extension of spin. It's a high version of the spin algebra, right? That is relevant in string. So you know, if you were considering spin structures on loop space, they correspond to string structures on space-time, and the corresponding string algebra is essentially one version of that is the one that you see up here. So you have spin n in degree 0 and you have r in degree -1, just like we had before. It's a special case of the Lie2 algebra that we have in the 4D transscience case, right? I just specialized here to spin n instead of L0 and r instead of L-1. And the structure that you have here is that mu2 is just a commutator on spin n, and mu3 is a Cartan-killing form that you get. You know the obvious co-cycle with the metric and the commutator next. Now, the two versions of the Weil algebra that you get, right? Remember, we defined the curvatures from the Weil algebra to the differential forms, and now it really matters which form of the Weil algebra you take, because the xi's are mapped to the potential and the shifted xi's are mapped to the curvature. So here it really matters how you parameterize your Weil algebra. So it's an automorphism destroys things, and the Weil algebra is fully contractible anyway. So here on the left-hand side, you see the conventional one that you would naively obtain that matches the homotopy Mauer-Cartan story and everything. And on the right-hand side, you see the modified version. And above, you see the Weil algebra for R hat, right? And then you see the transformed object. So R hat, we have some freedom there. R hat is a degree 3 object, and I can deform it by this kappa term that appears there, right? And anyway, so you see the left form, you see the right form. As differential graded commutative algebras, they're completely isomorphic. There's no difference between them. However, how they parameterize physics is different, right? So this is a little bit uncomfortable usually for mathematicians. But again, the Weil algebra is the Chevalier-Einberg algebra for inner derivations. Inner derivation algebras are contractible anyway. They're completely trivial. So if you want it, they're quasi-isomorphic to nothing anyway. So here it's really the parameterization of things that matters. Okay, so you do this modification, you do the shift in the Weil algebra, and then it turns out that the curvature is actually deformed as you would expect, right? So you see the two-form curvature has the usual form, but the three-form curvature has now an additional term coming from this kappa, right? Here the kappa is just the killing form, and the new term is such that the three form actually combines in the well-known transimus three form, so ADA plus A cubed, as you all know, right? And if you now apply DH, you get the correct Bianchi identity, right? So you see that you get very different physics depending on what parameterization of your Weil algebra you choose. And so this transformation that we introduced solves the problem. And that is crucial. That is actually what makes a difference between jobs with nice connections that actually work for physics and jobs with bad connections that don't work in physics. Right? So, and that small delicate point is really important. And if you look at Ur's paper at the time when he introduced that precisely for such L-infinity algebras, not in general. And it's very, very hidden there in the why you do that or what it does for you and what's the justification of so this. Okay, so let me talk a little bit more generally about this. So why did we actually have to perform this basis change? What's actually the reason for why that appears? So the problem is simply that the BRST complex for the original Weil algebra, which you can derive in a particular way, you have this Weil algebra, and essentially you look at all the graded maps from differential forms. So all the maps, not just the grade preserving one, but all of them into this Lie algebra. Mathematically speaking, you do the inner Hom there, right, in graded manifolds. And you consider all of them, you get essentially the BRST complex. There's a natural differential, that's the BRST complex. If you look at the BRST complex, it comes with a natural differential, but what you need to do is, because you doubled, okay, let me explain it in a little bit more detail. What we did here is, if you just map into that, you get connections and curvatures. If I construct the BRST complex in the way that I just said, I realize all the maps into this Weil algebra, I can get everything doubled. I get also curvature for ghosts and ghosts for curvatures, right? But that means I have way too many gauge transformations. I need to cut them down. And if you truncate the resulting BRST complex that's too large, you find that Q square is actually not necessarily to 0, but then you get these failure terms that actually are parameterized by the two-form curvature. This two-form curvature is also called fake curvature, and a lot of the high H theory literature you will find that for consistency we need to put this to 0, right? That's always a thing. And if you look at the higher power transport papers, they were developed by Waldorf and Schreiber, there you find that they always need to put the fake curvature to 0. Also, John Baez wrote a paper on this with us. Because otherwise the power transport is not very parameterization invariant, right? So you get issues there. Exactly here. So without this condition, the BRST complex is open, as I said, without f equals 0. Higher power transport is not parameterization invariant. And if you, like me, come from probably string theory motivation, you would like to have in 6-dimension self-dual free forms as a particular interesting object. But the self-duality is actually not gauge covariant, right? So if you have something self-dual, and you gauge transform in this picture, then it just transforms to zero. Well, it doesn't resolve itself to reality. However, if you impose this condition, if you impose the f equals 0 condition, as suggested in a lot of the literature, then higher connections are just locally abelian. And that's what physicists mean when they say higher gerbs, or non-abelian gerbs are useless, because they say, well, locally I can always gauge transform into the abelian case. Why should I care about all these technicalities involved in defining non-abelian gerbs, right? So that is exactly the point. That's the problem. And this is what physicists recognize really quickly by local computations. And this is where this bias against non-abelian gerbs.
Christian.
Yeah?
I don't really understand this q square equals 0 would be equivalent to this other equation. I mean, usually you should, if you have this q manifold where the gauge fields more or less come from, you should lift it to its tangent bundle, and there you have another differential, q plus d plus LQ.
Yes.
And everything squares to 0, and you have also this f in there.
Yes, exactly. I mean, this is just, you know, if you look at the gauge transformation, that how to quickly explain it, that also happens in the VD formalism, right? So if you look at homotopy Marquardt theory, you take the commutator of two gauge transformations, you see that they don't close to gauge transformations, they close into gauge transformations plus terms that involve the curvature, right? So whenever you do this high gauge business and you try to close gauge transformations, you run into conditions like this. I mean, that's probably something that we can discuss a little bit later offline or so, because it will be a little bit technical. And I don't have a pen here, so, but Thomas, very happy to discuss that further. It's just something that happens quite a lot. So if you just take, you know, the homotopy Marquardt theory, let me quickly go back here. I didn't write down the gauge transformations.
Yeah.
So this theory has gauge transformations. You take the commutator of two gauge transformations, you see it's not a gauge transformation. It's something.
Yeah, actually in our picture, it is Q bundles, it always works. You have the vertical automorphisms and they always close. But anyway, that doesn't matter.
I can discuss that a little bit afterwards. So I'm happy to call you later to discuss that. Yeah, it's just what you see here is that these things usually don't close, and that is really the reason why we did have to do this whole business of redefining things. Because once you do this redefining of the Weil algebra to get the correct Bianchi identity that physicists have known for 45 years at least, then everything works and the gauge transformation closes, right? So the message is essentially, with this adjustment, with this redefinition of the Weil algebra, all the problems go away, okay? And then you can find a mathematical definition of these adjustments locally and then also globally, and all your problems with the parallel transport, with Bianchi identities, with gauge transformations and closing, they just go away, right? So indeed, if you look at, for example, gauge supergravity and other theories in physics where high connections appear, you see that high gauge theories with adjusted curvatures are actually the ones that appear in physics. So whenever you see usually physical theory with higher degree forms and the way that they're defined, then it's the ones that have these adjusted conditions. But the BRSP complex that I didn't really give the complete explicit definition, but this thing so like this. Okay, so one example, for example, is gauge supergravities in arbitrary dimension. And just quickly, it's a theory with higher form potential. Physicists constructed by hand. They say, okay, we have a curvature that doesn't transform how we want it to transform, so we introduce a two-form potential and correct for that, and that curvature doesn't transform, and so on. So a little bit of a process, originally was constructed by hand. Later, they found that there's a differential created Lie algebra underlying it. And when you look at this a little bit more, you know, from a homotopy algebraic perspective, then you see that DG Lie algebras can be shift truncated to H Lie algebras, which are Lie algebras where the antisymmetry is essentially lifted up to homotopy. So a Leibniz algebra with additional datum. If you know Dorfman bracket from generalized geometry, that's exactly what it is. Right? And it's actually also exactly that construction. And such H Lie algebras, they contain adjustment data for an L infinity algebra, right? So before we had the Cartan-Killing form as an adjustment datum right here in the Weil algebra. More generally, if you are engaged supergravity, you have these H Lie algebras, and they have the additional adjustment datum that you need in. And here's an example. Don't worry what this all means. We can just skip this. But you see here in red, you see the various adjustment terms that are added to the action, and that guarantees that the gauge transformations close that guarantees that everything essentially works out as you want it. And if you then compare this construction that we have with the supergravity literature, you find that they're exactly the curvatures that people talk about, right? So these are the ones that people also recover by hand. Okay, but this is all local theory, right? Local is easy, and now let's go to the global picture, because topology is something that's usually very interesting in gauge theory. And after all, I mean, that's the point of going to non-abelian gerbs for you to describe also the total structure. In particular, we may be motivated from string theory, where we have T-duality, and then of course, once you start talking about T-duality, you need circle vibration, or something like this. So you definitely want non-trivial topology, and therefore you need to principal bundles, and you somehow need to extend that into something that's non-abelian gerbs. So there is a global picture that you can define. There's a very nice way of describing two groups, higher dimensional gauge groups, in terms of cross modules of Lie groups. So you have this cross module description here, HTG, describing two groups. And then an adjustment in this case is an additional map that satisfies these two properties, right? And that's work with Martin here and my PhD student Dominic already a while ago. And then you can really write down the full adjusted co-cycle conditions below, right? So these things that you see down here, they're the transition functions, the gauge potentials, and the gluing one forms on the various patches that glue together all this data into a non-abelian gerb, which is topologically really easy to define, but then also something that has adjusted connections on that, and where everything works, where gauge transformations close, where you reproduce with physics, and so on, right? So you can do that. I don't want to go too much into details because it will become rather technical, and I'll explain how to do that more systematically later anyway. So why would you actually care about that? Well, if you're a physicist, there's quite a few reasons. First of all, heterotic and gauge supergravity, you may want to put this not just onto flat space, but also on arbitrary manifolds, and you need something like this. Particularly heterotic supergravity is where we need this. Another very nice application is actually geometric T-duality. You can describe it as non-abelian gerbs, and this picture has been developed by Nicholas and Barlow in 2018. They have the topological part of geometric T-duality. It's essentially a span of principal two bundles or non-abelian gerbs with structure two group. But they never were able to differentially refine this picture because they didn't know how to define connections on these things. And the problem with defining connection is this adjustment trick. But we, of course, knew how to do the adjustment, so we did the adjusted connections, and then everything works, and it fits very, very nicely into this picture. And you get the various structure two groups that are involved. The one here has a very, very nice additional structure that it comes with anyway. That's exactly the adjustment. And finally, a mathematical example. So you probably know the instanton and how important it was for differential geometry and the development, right? All these constructions that surround instantons. There's the SU2 instanton, which is a particular principal SU2 bundle over S4. What you can do with this fundamental instanton, you can double it to two copies of SU2, right? So instanton and anti-instanton. Then you have a spin 4 principal bundle, because spin 4 is SU2 plus SU2. And this spin 4 bundle is exactly spin 5. The total space is spin 5, and spin 5 over spin 4, that's S4, right? That's the base space, right? So that is it. And what you can now do is you can take this spin 4 bundle and you can lift it up to what's called a string bundle, right? I mean, people knew from a topological perspective, topologists know that these things exist. That string group is very, very important. What you can do is you replace spin with a string, so SP with SPR, and you can argue that this here, I mean, string 5 is as topological group infinite dimensional, but there are certain two group models which are nicer to handle, right? So you can look at these as two groups. That means you have here two spaces. The quotient will still go down to S4, and this here will now be a non-abelian gerb, right? But for instantons, we are very interested in also working out the connections, because then you can define characteristic classes with Chan-Wei, you can define certain Chern character and so on. And here we want them to endow this nice categorified instanton with higher structures and with higher adjusted connections. And you can indeed do that. This one has an adjusted connection. This adjusted connection has f not equal 0, right? Remember, f is the curvature on the spin 5 instanton bundle, so it's definitely not 0, otherwise we wouldn't have an instanton. So here we need to use adjusted connections to describe that appropriately. And that you can do, and we wrote down the explicit example. So there are explicitly non-abelian gerbs that are interesting, because in particular they lift here the instanton. And from another perspective, you can also argue that they lift the monopole in particular. Anyway, so the summary so far, there's this widespread belief amongst theoretical physicists that non-abelian jerks do not exist or are useless. Both statements are just plainly wrong. The cause is much literature focuses on unadjusted connections, and that's the thing. Without adjustments, yes, the connections on them are basically useless, not very interesting, but with adjustment, you get a lot of interesting stuff. The adjustments and jerks are both mathematically well defined, there's no problem. And they solve a lot of physics issues, a lot of mathematical issues, and they're really the ones that we get from physics. And a lot of these sample applications, they work perfectly. So now the next step is then, of course, then explore the adjusted connections a little bit more generally and also more systematically. Because so far these constructions were a little bit by hand that I showed you, right? And also the justification of what we did was a little bit by hand. Yeah, now I come to this Atiyah Algebroid replacement. I hope people forgive me that I'm not working with the Atiyah Algebroid. And that's work for the Groupoid case by Saemann Fischer. So Saemann is Thomas' ex-PhD student. Meran, my PhD student, Jan Rock, who's now at Hertfordshire, my ex-PhD student. And yeah. So as I said, above constructions were very much by hand, but as you all know, John Bias told us that category theory is a subject where you can leave the definitions as exercises. So essentially, you should be able to crank a handle and all definitions should pop out. I shouldn't be working, right? I should be working to work out what the definition is, but there shouldn't be freedom, right? There should be a natural path towards the definition. And that's the one that I would like to explore. And also, so far, only we have very partial insights into the origin. Where do the adjustments actually come from? What are they actually? And I showed you one, namely that a lot of infinitesimal adjustments come from these H-Lie algebras that we encountered in supergravity. So where the gauge algebra was obtained by shift truncation of a differential graded Lie algebra. So there are some situations where you have something natural, but we don't have a picture in general. And also, I should say that for certain two groups, adjustments exist, but there are also two groups for which you don't have adjustments. So for which you cannot define nice notions of adjusted connections, right? And then also the questions of course, what about general higher gauge theory? So how can I write something down that works always and not just in particular settings? Okay, so we want to construct non-abelian jerks. So the total space description of a non-abelian jerks is pretty much easy, right? So if you have a higher space or higher groupoid with the principal action of a higher group, so category theory tells you how to define that, and you have various versions of weakness there, and that's all fine. And in principle, you could now branch off and define connections as connections on the total space of this bundle, right? And then do the usual stuff with, you have patches, pullbacks, or whatever, right? So you could have a total space prescription of connections, but then that's not what I want to do. I'd rather stick with cocycles, and the reason for that is simply because I want to use them in physics. I need to do computations with them, and computations are usually done over patches of manifolds, right? And I want differential equations there. So it's a little bit more convenient if you come from a physics perspective to have that. Topological cocycles are also very easy to define, right? You take the check groupoid, but so you have a surjective subversion from one manifold to your base manifold of your bundle, and so think of it as a cover, and then you construct a groupoid consisting out of that cover and define a product of the covers, so the overlaps of these local patches. And then it's just a functor into the delooping of your gauge group, which is essentially just a groupoid that has one object and G as its morphism, right?
So, Christian, why topological cocycles instead of smooth ones?
Well, okay, sorry, that's the topological information. Not the differential refined ones. Yeah, sorry. I could say smooth cocycles.
Yeah, because you use subjective submersion. So
yes, sorry, yeah. It's a bad idea. Okay, so the thing that doesn't really work is the splitting of the Atiyah Algebroid sequence, right? That we already encountered, but maybe we can do a little bit better. First of all, I would like to reformulate the Atiyah Algebroid a little bit as a DG groupoid. Recall from the local description where we mapped differential forms into Weil algebras that we used a lot of DG language, and that was very successful. So perhaps it's good to use DG language also here. And in the local description, also remember that from the flat case to the general case, I need to extend from the Chevalier-Einberg algebra to the Weil algebra to double things, to essentially resolve this failure of the maps to respect the differential. Okay, and then also because I'm a little bit physicsally minded in that, and I'd like to have cocycles, differentially refined cocycles. What I can do by Morita equivalence, I can replace the manifold itself by the check groupoid, right? The manifold regarded as a groupoid is Morita equivalent to the check groupoid. So essentially I haven't done anything by doing this replacement, just use the weak morphism of groupoids. And then correspondingly, I can also replace the Atiyah Algebroid actually with this DG groupoid that is over there, right? So it has a natural DG structure, it's graded manifold, there's a grade shifted tangent bundles appearing, and it has a differential structure. What you then have, once you see this, is that there's actually a natural DG action of T1G on the Lie algebra itself, here seen as a Lie algebroid over point. This is why that's written as G1. And this action is just given in this particular line here, right? So here you have an element in Lie algebra, and here you have an element in T1G, G, and gamma, an element in phi over G. And this is just the action. And you, of course, if you know gauge theory, you recognize this as looks very much like a gauge transformation. And that's actually the point, right? So from this, you can combine the data into an action groupoid. So the action groupoid that you have is you have the objects are just it's just a Lie algebra, and the morphism, of course, is T1G action on the Lie algebra itself in the obvious way, right? So this groupoid describes the action. And if you, once you have that, you can ask, okay, what does that have to do with the Atiyah algebroid? Well, the Atiyah algebroid is nothing but the pullback of this action groupoid from T1 VG to the check groupoid, right? You see this in the lower diagram. So the lower line of this diagram is just a map that we had previously. So probably not too fast. So where I wrote it inappropriately, topological co-cycles, you see that I map from the check groupoid into BG, right? And this functor defines the transition function of my bundle. If I now go here, what I did in the lowest line of this commutative diagram, of this pullback diagram, is that I just lifted this up to the tangent spaces in a unique way by saying, okay, there's a DG mapping along this line. And now the Atiyah, this action groupoid that I've introduced, sits on top of T1BG. And if I pull back this along DG, then I get precisely the Atiyah algebroid. Okay, so that's just an observation, and you do the computation. It's not particularly difficult, and you have it. So how do you define, or how do you construct this action algebroid a little bit more systematically? So what you have is there's this famous Lie functor suggested or described by Chevera in 2006 already. And what it allows you is to differentiate groups, simplicial groups, or anything, well, higher groupoids actually, to Lie algebroids in the form that you get the Chevalier-Eilenberg algebra. There's here the example of the differentiation of a Lie group. It's a little bit technical, let me not go into there. But what the action groupoid that I introduced above simply is in general, is the inner homomorphism groupoid of this construction, right? So here, in this case, you get functors from these inner homes that appear in the line on moduli here. These are functors from this particular check groupoid into BG. If you have functors, of course, you have also natural transformations. And so instead of looking just at the inner homes functors, you form a whole groupoid out of these, right? And this is what this action groupoid ultimately is. And that tells you now also how to define it for higher groups, because for higher groups, you will get a higher inner home 2 groupoid or 3 groupoid and so on, right? So you get a very natural construction there. Okay, so and now we replace the Atiyah. It did its job for us. Okay, so we have the Atiyah algebroid as a pullback. How do we define connections? Well, connections are actually splittings of this Atiyah algebroid sequence, which correspond precisely to the splitting of this map here, right? But if I split this map, so if I map from T1 check into Atiyah, then I can immediately continue it with the map from the Atiyah to the action groupoid, right? So instead of looking at splittings from here of this map, I can directly map from here to there. And this is indeed the same as the co-cycles of a principal G bundle with flat connection. Okay, so it's literally the same. The flatness is not surprising because we work in our DG category. We work with DG maps. And remember that the curvature is actually the failure for being DG morphism. So we'll have to work a little bit harder. But here we get flat connections just by these DG maps. And this description is completely in terms of usual local co-cycles. So physicists are happy because you have transition functions, you have local connection forms, and you can calculate with them. You can write down the field theory. And yeah, we can circumvent the Atiyah completely, and instead we can use this action groupoid for flat, right? So co-cycles for principal G bundles plus flat connections are DG functors. And the other reasons for replacing them, at least for Groupoid bundles, we had a discussion this morning, I don't think that Ben will be, but I'm pretty sure that for Groupoid bundles, this Atiyah is a little bit complicated. Okay, let me give you a quick example because it's all very abstract. So a principal G bundle with connection G is Lie Groupoid. So this action Groupoid that you compute from Chevera or just write down is given by this. And now bundle with connection I claim is a DG functor from the tangent of the check Groupoid into this AG. Yeah, and the maps that you have are the following. So on top, at the level of morphisms, you have both A and DG. So DG is just a lift of the transition function in the evident way, in the unique way to the corresponding differential. And then in addition, you have the local gauge potential that you have. The compatibility with the differential Groupoid structure then gives you exactly how these things should glue together. Yeah.
Shouldn't this be the Marok-Bertrand form instead of DG?
No, that's it's really DG, right? So remember, G is the map from Y cross MY to G, right? And DG is just a lift to the tangent bundle, right? And then in addition, you have this map into G1, which is just induced from the identities down here, right? So you get literally the linearization. Right? And compatibility with the differential as expected gives you flatness, right? So this is all good. So in this sense, we have now a new description for flat connection, which we can immediately translate to higher bundles. Right here, everything is clear how to do higher. Namely, the only thing that you have to do is you have to replace this action Groupoid by the higher action homomorphism Groupoid that Chevera tells us how to construct. Right. So it's a very natural object. You can compute it. It's not difficult, and then you know how to do higher. Okay. So still no adjustments so far, but we work in the flat case. And flat case, we never see adjustments. Right. Okay, so now beyond flat connections. How do we go beyond flat connections? From the local picture, we recall we needed to double the Chevalier-Allenberg algebra to the Bay algebra, right? The Chevalier-Allenberg was not enough to do DG, right? The flatness was essentially that it's compatible with the differential, but once we lift it up to the Bay, it works, right? So then what you would be, remember the transition from Chevalier-Allenberg to Bay was just that you use T1 of G, the Chevalier-Allenberg of T1 of G. So here the obvious thing is to use, well, how about using Chevera for T1 of the group? And then you get indeed a Bay algebra for G, that's fine. However, this action Groupoid can be computed, right? So A of T1 of G instead of A of G can be computed again in the same way, and you now get a differential graded Groupoid out again. And bundles and connections could be regarded then as such morphisms. However, the problem is that this produces too much. And what does it produce too much? Well, it produces exactly as in the infinitesimal case, it produces also gauge transformations of curvatures, right? So instead of just being able, instead of just having gauge parameters for potentials, you also get gauge parameters for curvatures, which is just too much, right? So you need to cut this down, right? And the solution is here, this triangle in the lower left corner. So what you have is you have the AG, the usual action Groupoid for flat connections. That should certainly embed into the, or does naturally embed into T1G, in the larger one that gives us too much. And what we want is something in between, this AW, right? And so what we're looking for is now this AW. And the question is how to define it. And Meran came up with a very nice idea of how to define it. The condition for AW is simply that it pulls back to this particular expression. So on the right-hand side, for people online, you have this pullback diagram. And what you want is that AW pulls back to this particular expression over there, where you see on the left-hand side just the action Groupoid that we had before. On the right, you see the generalization. What this ensures is, first of all, that flat connections are properly embedded into non-flat connections, but it also ensures that you have the correct amount of gauge transformations, because this T1G at the top left corner of this pullback diagram is exactly the gauge group that acts on that. And these are the right. This is the right set of gauge parameters that you want to preserve, right? So as soon as you have the pullback, everything works. And indeed, you can then go through the exercise, and that explains, I mean, this restriction, finding AW instead of AT1G, and ensuring that AW is nicely defined, that's exactly what induces the adjustment, right? This is where adjustment comes from, because you can't just double, you need double, and you need to restrict carefully. I can give you probably briefly the my watch has given up already. Give you the example for two group. Yeah, so what you have is, if you look at the two groups, this is AT1G. That's the thing that is too big. And this is all the data that's associated to the various elements in there, right? So don't look at it in detail, it's not that important. What you see is, for example, here in the middle line, the last element, you see a Gij, a dGij, and G bar, dG bar, right? So the differentials are all fine, they're fixed, right? Once you have a map, you know what the differential is, that's not additional data, we can have that. But all the second copies that we have, they need to be constrained. We want to get rid of them in a consistent way, right? And all these bar objects essentially should go away, and either we can truncate them without any problem, or we have to define them in terms of other cocycles consistently, right? And this consistent definition is precisely what an adjustment is. And then you can show this theorem that if you have this Groupoid plus DG structure, that the kappa has to be an adjustment for strict two group. So this construction that we had by hand of the adjustments, what they actually are, they drop out here directly out of this consistent truncation business of this group. Okay, so and then there's now this general systematic prescription of how to define principal bundleless connections in the form of local cocycles and relations. And of course, you get H transformations, so bundle isomorphisms out of it as well. Okay, because I'm running out of time, let me talk a little bit at least about the Groupoid H theory. Namely, what if you don't believe in string theory, you're not interested in supergravity or even the more esoteric high H theory, should you still care about adjustment? And the answer is still yes. And here I regret a little bit that I didn't know that Thomas was on the call, because I was a little bit succinct in the history of these things, because these observations that you need to do something, that goes back to Thomas' paper on Algebroid Yang-Mills theory from 2004, I think it is. And he found it first, and then he has follow-up work in 2015 with Alexei Kotov, sorry, Alex Kotov. And yeah, so the adjustments also appear in Groupoid H theories. Yeah, so what's a Groupoid bundle? Recall how principal bundle is defined as a functor from the check Groupoid into BG. Principal Groupoid bundle is just a functor from the check Groupoid into the Groupoid, into the Lie Groupoid that you're interested in. Right? So the definition at the at the level of just cocycle is clear. It's just a question of how do we actually put a connection on top of that, right? So yeah, physically, this map into G0 is usually seen as a scalar field or Higgs field, right? And we then gauge it in physics lingo, and the gauging is, associating a principal bundle that has local connection forms associated with it. The examples are Yang-Mills matter theory, associated vector bundle and group actions roughly, but then mostly gauge sigma models. So, but of course, in both of these cases, physicists implicitly use Groupoid H theories, but very, very simple forms of groupoids. But there's no reason why you don't use also much more general groupoids. And then you can ask, okay, why should I care here about adjustments? Because we have exactly as in high H theories, where we have true form curvature F and free form curvature H, we have here also two levels of curvatures. Namely, we have the true form curvature F from our connection that we have in there, but we have also the covariant derivative, which is like a curvature of the scalar field, right? And so because of these two levels and their interaction, we need again to do an adjustment. Okay, so here, no, sorry, Thomas, I actually do cite you. So first observed were these locally by Thomas and Alexei. See also a little bit Simon's work on this, which is very, very nice actually. And yeah, so fake flat connections are readily defined, and these non-fake flat connections, they actually require an adjustment that is a particular form of connection on the Lie Algebroid, and an additional datum that you need then if you want physically to define actions. So what did we do about this? Well, Hyunwoo Kim, my PhD student at the time, published his PhD thesis on the archive, and then Simon contacted us and said, oh, these adjustments look like something that we actually have as well, right? And then we decided, okay, why not try to work out the full thing in globally, right? I mean, the local story is done by Thomas and Alexei, and globally, you can use exactly the same procedure that I introduced above, right? So you construct this action groupoid, and you consider again maps from the tangent bundle into this action groupoid, right? So this procedure that you here see, the general systematic prescription, works exactly in the same way. There's no difference whatsoever. It's just that instead of having G1 as a Lie algebra, it's now a Lie algebroid, right? And the formulas get a little bit more complicated because everything is locally over points. You have differential relations as well. But this procedure works now. You know that it works for higher gauge theory and it works for groupoid gauge theory. So we expect it to work also for higher groupoid gauge theories. And then something very nice comes out of this story that was known at the local level, certainly, is that an adjustment of a Lie groupoid. So the additional data that you need to define this action groupoid that I had, this truncated action groupoid, is what's called the Cartan connection on a groupoid. Okay, so Cartan connection on a groupoid is a multiplicative connection. So it's roughly a splitting of the differential of the target map, so the tangent space there, into horizontal vertical subspaces, which is compatible with the composition in the groupoid. That's what this is, right? So here we have something really, really nice because it tells us what an adjustment is in the groupoid case. And now the temptation is to turn this around and see this as a definition for connections for higher Lie groups and higher Lie groupoids, right? That they should be exactly what an adjustment gives you, right? And that's something that we hope to explore in the future, but I'm out of time, so I should probably just sum up. So the summary is non-abelian germs exist and they're non-trivial. The big message, right? So nobody forget about that. Then I showed you a fully systematic way of constructing these adjusted co-cycles, adjusted connections. Personally, I'm now very happy with adjustments. I know where they come from, what they do, why they're there, and I know how to work with them. And the framework is essentially ready to apply to any situation that you have, right? So we are there, the mathematical groundwork has been laid. The adjustments also appear in these groupoid gauge theories. And the last point was this observation that it seems that these adjustments are connections on higher gauge groupoids. This is not too surprising, and if I can just quickly show you that, because you remember what did we actually do when we adjusted? In the Weil algebra, we performed a coordinate change in such a way that we redefined the curvatures. The curvatures are kind of the vertical part in the Weil algebra, and the connections, you know, the headed objects are the curvatures, they're the vertical part. The connections are the horizontal part. So this definition of what is curvature, what is connection, is really like a splitting of the tangent button, right? It's like a connection, and this is exactly what appears here, right? So that's what we have here again. So Outlook. So we're currently developing. It's an absolutely brutal computation, and I feel sorry for the PhD student who assigned it to, but I'm helping, so just leaving it. So we have explicit formulas for principal of three bundles. The reason for that is we simply want to describe U-duality, you know, the lift of T-duality to M theory, and there you have three forms around. So at least you need some form of principal 3 bundles. Ideally, you need actually principal 6 bundles because you want a democratic formulation like that. This is also very interesting for phenomenology, as first pointed out by Thomas, of course, and Thomas' first paper is published in First Red Letters, even though it's quite mathematical with Groupoid or Algebroid gauge theory. But of course, what you want to ask, is there a new Higgs mechanism behind that, right? Can we do something more? And yeah, we're currently looking a little bit and playing a little bit around. You know, the standard model of elementary particles is of course a groupoid gauge theory, right? So but it has a very simple groupoid. It's just an action groupoid. And you know that a lot of people are now looking for deformations of standard models where you can get new physics from. So maybe if we choose a clever groupoid, or here actually it's just because it's local, if you choose a clever algebroid, then we can get something interesting. And I think Thomas has also been looking there. I guess, Thomas, you haven't found anything until now, but you can tell us later if there's anything around. Yeah, and well, then the adjustment data I presented as additional data on the gauge groupoid. However, by now we have just recently found out that there's no cyclic adjustments. So if you have an L-infinity algebra that's cyclic, you can't find adjustments. That puts that a little bit into a question mark around this, and maybe we have to be a little bit more general. But we found new forms of hydrogen science theory, which are quite interesting. And then what I mentioned is that we turn this around, that adjustments are actually connections. We can now see, okay, what's an adjustment on a Fourier algebroid, which will give us a new notion of connection on a Fourier algebroid, right? So things like that are now open to explore and probably to have fun with. Okay, but thanks very much for your time. Thanks very much for your attention.
Very interesting. Thank you very much. And now let me open the room for your questions.
So far,
so maybe I'll have the first piece of questions. You introduced the factorial approach to constructing Atiyah Algebroid. And do you have any insights how to factorially conceive the adjustment itself, or how this gadgetry goes into the construction?
Yeah.
Or
so I mean, I use the factorial approach to say that well, the Atiyah Algebroid is a pullback of a particular DG Algebroid, and the point with the adjustment is you need to replace that if you want to do non-flat ones, because for flat ones everything works. You never need to adjust flat things, right? Flat are all good because that's what the our theory. But so you want to construct this AW, and the construction of this AW requires an adjustment. It's essentially, once you have a consistent AW, you have an adjusted groupoid, right? So that's a DG groupoid that needs to fit into this pullback. To be able to fit into this pullback, you need additional geometric information that allows you to define the algebroid, right? And for lead groupoids, for example, it's exactly a cut-on connection that you need, right? And for two groups, it's this kappa that you need, right? So it's essentially the data that you need to cut down from here to AW. That is the adjustment.
Is it canonical?
No, because adjustments don't necessarily exist. Right, so you can have, I mean, on groupoids, yes, you can. I'm not sure actually if every groupoid has a cut-on connection. I would guess so, but at least for lead two groups, we know that there's certainly two groups that don't admit an adjustment actually. And then you can do various tricks, because you can go to you replace it with another group so that the classifying space are homotopy equivalent, and then on the larger bundle you can then define adjusted connections, right? That's something that actually happens in the T-dual example, that you know the little ones that don't have adjustment, but the big one has an adjustment, right? So that's something that happens there. But yeah, it's not canonical, so you kind of tease out what this is, but the guess would be that this is a nice. I mean, for ordinary principal bundles, there's no adjustments, right? It's only whenever you have two or more levels of connection forms, and here you would expect now that well, it defines for you what the connection on a two group should be. Right, so I mean, there's an obvious notion that you can write down. It doesn't quite work. You need to tease it a little, twist it a little bit. But because we saw that you get cut-on connections on groupoids, right? So a notion of connection is actually the adjustment. That's a picture that's emerging from here. We haven't completely done it yet, but it's pretty clear that this should be the case. But yeah, not everything apparently admits a connection, right? So yeah,
maybe one additional question or remark. I saw how you came up to the construction of the Atiyah, and there is also one kind of traditional approach of constructing W of Atiyah. You can factorize your cocycle morphism into epimorphism and monomorphism, and the vertex you obtain is nothing but your W of Atiyah, which is some co-limit of iterated pullbacks. So there is a chance to see this result maybe from different perspective. When you roll the whole diagram and you just apply Shivera functor as to descend from groupoids to algebroids, and see whether this has some relationship to.
Yeah. No, absolutely. I mean, here, to be honest, the reason why we replaced Atiyah was just we struggled with the Atiyah Algebroid. You know, I mean, the naive definition TP over the group for groupoids. The thing that we found is that you don't get at least in the general case, you don't get vector bundles. Right?
It was my struggle as well.
Okay, right. So maybe we arrived at the same, and then we came up with this. Well, how about just circumventing Atiyah? And then yeah, I mean, this seems to work, and Meran likes his DG morphisms very much anyway, so it was a perfect match.
Very nice, thank you. So, further questions? Maybe from online audience or?
So maybe can I ask another problem with the cyclicity?
Yeah.
So is it something that can be solved, or it sounds at first it sounds like drastic, right? Like if you just want to quantize it, be the single structure. So
yes, exactly. I mean, the answer to this is in the examples that we saw, the adjustment was a pure data on the gauge group, right? And everything else was then induced because you had the gauge group, was the structure group, was the principal bundle, everything else was induced. But this is actually not necessary for field theory, right? Because in the field theory, there's weird things happening. If you do higher transience theory, you saw that this arose from the gauge L-infinity algebra tensor the differential forms, right? That automatically means, if you take quasi-isomorphic L-infinity algebras, you get quasi-isomorphic field theories in the BB sense, right? So the BB, the L-infinity algebra dual to classical BB would be quasi-isomorphic, right? But this is actually not true for a lot of high gauge theories. So if you look at high gauge theories, you cannot factorize, right? This is what physicists would call color stripping or something like this. That doesn't exist for a lot of high gauge theories. It's even worse. In a lot of high gauge theories, the gauge algebra is actually fully contractible. You'll see, if you look at these generalized symmetries, for example, you see that there is a high gauge theory underlying it that has seemingly injective maps from L-1 to L0, right? And injective things you can always you go to the minimum model and get rid of them. They shouldn't be physically relevant. However, because the theory is not a tensor product, so it doesn't, the L-infinity algebra that we get as a field theory doesn't respect quasi-isomorphism of the gauge L-infinity algebra. Therefore, you get physically non-trivial content, right? Which is really disturbing at first if you see that. So you have to be careful which representative in the quasi-isomorphism class of your gauge V L-infinity algebra you choose, right? And once you realize that, then you see, well, I don't really need the adjustment on the gauge algebra, but it's enough to have it on the L-infinity, on the total L-infinity algebra that I construct, right? And that's the solution. And in this way, it is actually quite interesting. So a couple of friends like Alex Schenkel and so on, they were interested in higher transience theory to do the Costello story, right? So, and I'm not sure, he might have given me a talk about this also. But he was exactly stumped by that. So he came then to us and said, oh, I like your cyclic structure because that should be the way how you define the action properly without degeneracy in the variation and so on. But I can't find examples with that cyclic structure, right? And then we showed actually there's actually no such things. And that's what came out. But then we looked a little bit more into it to make this comment and point this out. Please don't look there, there's dragons, you can't find anything. And then we found, well, forget that it's on the gauge algebra, just define it on the theory and then it actually works. So you can find higher transience theory that are adjusted, that fully work, where everything's okay, and so on. And these now lend themselves of doing, this higher transience theory from Costello in higher dimensions, right? Exactly. Yeah, so at first it sounds a little bit scary, but to be honest, you can never get adjusted field theories from tensor products of the gauge algebra or something else, because you have this ADA, these additional terms which have both a product and a differential. You can never produce them, right? So that doesn't work. It's something weird that I don't quite understand. It's just a fact of life, but no color stripping of physics. So gauge equivalent, well, the isomorphism of gauge algebras give you new physics, which is weird, but unfortunately true. Yeah.
Thank you.
Any further question?
Maybe I can make a small remark.
Sure.
So I think if I understood correctly, your generalized Atiyah algebroids are just these Q bundles. And then there's this generalized Weyl map which you construct with Alexei. And actually nothing there changes when what you call is adjustment. So the connections are actually in this generalized Weyl map in there. And if one wants to indeed construct these invariant action functionals, what we considered with Alexei but didn't publish yet, I told you once, is to work on this target Q manifold. And the idea there would be to do a reduction of the structure group, but in this graded structure group. And in this way, one can understand geometrically what this adjustment means. But I would still like to stress it has nothing to do with the connection. The connection is this section in this Q bundle.
No, but you get different gauge transformations, right? So you get different bundle isomorphs. They act differently on the connection.
No, the gauge transformations are these vertical automorphisms of these bundles.
Yeah, but I mean, the difference between unadjusted connections and adjusted is exactly that the gauge transformations are modified. Right? So you see in the flow cycles, they're
no,
really
you just need automorphisms, and they certainly need to respect. If you made some splitting in the target queue, they need to respect this.
Yeah, no, maybe, but I don't know the Q bundle story that well. But you know, if you say that you can reproduce these adjusted connections in your language, you should see that the gate connection actually change.
Yeah, it follows from this picture. That's what I want to say.
Okay, yeah, that's nice. But because you get different gauge transformation, you get different Bianchi identities. Really, I mean, the physics for adjusted connections very.
But in our picture of this Q bundle, the gauge transformation are just vertical automorphisms. That's a nice thing.
Okay,
always that. You know.
But so something that I didn't understand in Q bundle, you say that you can do global things without problems, right? Everything glues together.
I mean, like the Atiyah algebroid, it knows about if the bundle is non-trivial, but it doesn't contain the whole information about a non-trivial bundle, but part of it. So
okay, that's interesting.
And the characteristic classes we have for these Q bundles, they are generalized the usual ones. So that was the idea of this generalized Chern-Willman.
Okay, right on. Can I quickly ask you, have you made progress with finding any interesting groupoids for phenomenology? You know, for these Algebroid gauge theories?
Actually, we have a kind of a different type of result, which we found a Lie groupoid, which okay, let's say like this: we have a singular foliation which is known to be non-homogeneous, so not equivalent to a G action on it. And we also found a Lie groupoid with my student Hadi Nahari, which generates this. But it turns out it's not a singular Riemannian foliation in the strictest sense needed for gauge theories. So I wanted to construct this example, but that one we have is not such an example. And it's still interesting that there's a difference between usual singular Riemannian foliations and the ones we defined, which are needed for these gauge theories.
Okay, excellent. Now maybe we can talk offline then a little bit more.
Sure. Okay. Thanks for the talk.
Thanks.
I would have maybe another bit annoying question. I'm aware of your paper from 2016. There you also discussed cases of higher base spaces.
Yes.
I think this procedure is ready for this.
Yes, absolutely. It's very easy because the only thing that you do for high base spaces is you replace the check report with something appropriate for high. So that's really literally all you need.
Yeah. So you resolve some higher spaces in the same way how you resolve from ordinary manifold to.
You need categorified covers and so on. You construct
some hypercovers or.
Yeah, you get double groupoids essentially, and then you turn them, and whichever you prefer way, it's either you work with double groupoids or you turn them into bigroupoids, you know. Exactly. But yeah, I mean, this language is really universal in the sense that once you constructed this A1W, you just follow. Oh, sorry, but that's the general. The systematic approach is down here, right? And the only thing that you replace is check groupoid. So it's completely decoupled from the gauge story. And that works. Right? Of course, to get something interesting for higher spaces, you want at least two groups so that you get bigroupoids. Otherwise, it's a little bit boring.
Thank you.
Thanks. I think we kept everybody long enough.
Let me thank the speaker again for nice.
Thank you very much.